In chapter 7, we're going to look at how to develop optimized solution for a model that we've already set up. So you have a model that's running fine, simulation model, and then you want to study or analyze the model based on several possible scenarios and select the best outcome, best solution from those scenarios. So that's your optimization and decision making chapter. So we will be looking at a single case here, that is airline pricing model, and we'll use a technique called revenue management pricing. So you'll have two different pricing levels, and how do you allocate the number of seats for the two different pricing levels that will maximize your revenue. Okay. So that's the uh, basic model. Okay. So we're going to set that up and then simulate the sales of different uh, sales of seats at different pricing levels. So the first approach for optimization is to just simply run scenarios using risk sum table and select the best. Okay. Obviously, risk sum table is very limited, so you can only consider a handful of possible values. Otherwise, it becomes really complex. And what if you have several decision variables? Risk sum table maybe is okay if you have one or two decision variables, but if you have 5 or 6 standard decision variables, it becomes really cumbersome. So we At-Risk offers you an optimization optimizer to do this. And so with that, we look at the components of optimization. So there will be like, okay, what is that you want to maximize or minimize? So profit means you want to maximize. If it is cost, you want to minimize. And then what are the decision variables? What variables will have an impact on that, on the outcome that you're looking for, profit or cost or whatever. Then there may be some constraints. So you may have constraints like how many seat, in the airline seat management, so pricing model. So you cannot have more than X number of seats here, X number of seats there. So there may be some constraints, and how do you incorporate those constraints? So we look at all of those different concepts, and also local versus global optimum. So depending upon the function, the nature of the function of the output variable, what you find may or may not be the best solution. It may be best in a local sense, but not best in the global sense. So we'll look at the concepts behind local versus global optimum. And then we will actually use risk optimizer to find the best decision variables. The risk optimizer has to be used in an intelligent way, and we'll call that a progressive search technique. Okay, we'll talk about that. And then we'll talk about adding constraints to the risk optimizer. Then in that process, we can develop, using the risk optimizer, we can develop what is called efficient frontier of solutions. So that's like risk reward analysis. So if you are prepared to accept a certain level of risk, then at that risk level, your reward, what is the maximum reward that you can achieve. So determine the maximum reward for each level of risk. So you consider several levels of risk, and then you plot the maximum rewards that you'll get at all those different risk levels. So that is called an efficient frontier. So maximum revenue now in our airline pricing model. So maximum revenue given a ceiling, a maximum amount of standard deviation. So if you run the simulation and you have say 10,000 times, you have 10,000 revenue estimates. So there is an inherent standard deviation in that. So the more the standard deviation, the less reliable your estimates are. Okay, like if you look at the 90th percentile, so the 90th percentile, if the standard deviation is high, the 90th percentile may be more or less than what you have in the data. So you say, okay, all right, I will accept, say, standard deviation of 10, okay, or 11, or 12, 13, 14, and each of those standard deviation limit, then you want the maximum revenue. So that's your um, efficient frontier, and we will look at an example of how to develop that.